This is Objective 3 of Section 1.2, Power Functions. A function of the form f of x equals x to the a, where a is constant, is called a power function. We consider several cases. First case is that a is n, where n is a positive integer. 1, 2, 3, 4, da da da. The graphs of f of x equals x to the n for n equals 1, 2, 3, 4, and 5 are shown in Figure 11. These are polynomials with only one term. We already know a couple of these. We already know the line y equals x. Okay, so a is 1 in that case. A line through the origin with slope 1. And y equals x squared, a parabola. We know that one well. Here they are, and y equals x cubed. I'm sure you know that one as well. The cubic parent function. X to the fourth. I'm sure you know that one as well, and x to the fifth. The general shape of the graph of f of x equals x to the n depends on whether n is even or odd. Actually, in the first quadrant, it really doesn't even depend that much on that. They all kind of look the same. If n is odd, then f of x equals x to the n is an odd function, okay, not coincidentally, and its graph is similar to that of the cubing function. If n is even, then f of x equals x to the n is an even function, and its graph is similar to that of the parabola, or similar to the parabola y equals x squared. Notice from Figure 12, however, that as n increases, the graph of y equals x to the n becomes flatter near 0 and steeper when absolute x is greater than or equal to 1. In other words, on the outside of the box, okay, it's steeper. That is outside to the left, to the right, and to the left. But inside, in here, it's flatter. And that's true also for the odd ones, right? Steeper when absolute x is greater than or equal to 1, but then in the middle it's going to be flatter. If x is small, then x squared is smaller, right? Let's let x be 1/2. Okay, so x is 0.5. Then x squared is half of a half, which is a quarter. X cubed is even smaller. That's half of a half, which is 1/8. And x to the fourth, which is this red one here, is smaller still. That's half of a half, or 1/16. Well, another case is that a, right, power functions, y equals x to the a. What if a were 1 over n, where n is a positive integer? So 1/2, 1/3, 1/4, 1/5, 1/6. the function f of x equals x to the 1/nth, which is the same thing if you remember your rules of exponents. The nth root of x is a root function. For n equals 2, it's the square root function, right? When you got a square root, the index is 2, whose domain is 0 to infinity, and whose graph is the upper half of the parabola x equals y squared, right? X equals y squared, that's your sideways parabola, and the upper half of it is square rooting function. For other values, even values of x, it's going to be similar. Square root of x, fourth root of x, sixth root of x. Now, for n equals 3, we have a cube root function. The domain is a set of all real numbers, because any real number can be the input for the cube rooting function. Unlike the square rooting function, you can't take a square root of a negative, but you can take a cube root of a negative. So the domain is R, and graph is shown in the figure below. The graph of y equals nth root of x for n odd, fifth root of x, seventh root of x, ninth root of x is similar to that of the cube rooting function. What if a is -1? Okay, let's consider that case. The graph of the reciprocal function f of x equals the negative first power of x, which is the same as 1 over x, right? A negative exponent in the numerator is the same as a positive exponent in a denominator, is shown in figure 14. Its graph has the equation y equals 1 over x, or xy equals 1, same thing, right? If you multiply both sides by x, you get xy equals 1. It's a hyperbola with the coordinate axes as its asymptotes. So x-axis is a horizontal asymptote, y-axis is a vertical asymptote. The old reciprocal function, also known as the rational parent function. This function arises in physics. So here's an application of the rational parent function, the reciprocal function. This function arises in physics and chemistry in connection with Boyle's law, which says that when the temperature is constant, the volume V of gas is inversely proportional to the pressure P. So volume is inversely proportional to pressure. When pressure increases, volume decreases, and when pressure decreases, volume increases in a particular way, where C is a constant of proportionality. Thus, the graph of V as a function of P, volume as a function of pressure, has the same general shape as the right half of figure 14, right? The rational parent function.